March 15, 1943. A field hospital tent outside Gafsa, Tunisia, 30 miles behind the lines where the U.S. Second Corps is locked in a brutal contest with Rommel's Afrika Corps. Inside, under a single hanging lamp, a surgeon leans over a young infantryman whose left thigh has been opened by a mortar fragment. The wound is deep, packed with soil and fabric, and already the tissue at its edges has begun to discolor. A crepitant hiss escapes when the surgeon presses the flesh, the unmistakable sound of gas forming beneath the skin. Every textbook this surgeon trained from says the same thing. When gas gangrene takes hold in a limb like this, amputation is not a choice. It is a formality. Cut high, cut fast, or watch the infection climb towards the heart. But tonight, for the first time, there is something else in the surgeon's bag. A small vial of brownish powder, dissolved and drawn into a syringe, is injected directly into the wound. The soldier keeps his leg. He walks out of that hospital 6 weeks later on 2 feet that, by every rule of military medicine written before this war, should not still be attached to his body. This single decision, repeated in field hospitals across North Africa and then Sicily and then the beaches of Normandy, would rewrite the maths of survival for the wounded soldier. It would also expose with brutal clarity the gap between an army that had solved the oldest problem in battlefield surgery and an army that had not. What follows is the story of how a mold found on a rock melon in an Illinois market, a Scottish laboratory accident, and an American industrial machine combined to save hundreds of thousands of limbs, while on the other side of the front line, German surgeons kept sharpening their amputation saws. It is a story that turns on chemistry and industry as much as it turns on courage under fire, and that is precisely why it deserves telling. The soldiers who survived that spring in Tunisia rarely knew the names of the men and women who had made their recovery possible. The pathologists in an Oxford laboratory, the technicians in an Illinois research station, the engineers who built steel fermentation tanks the size of small houses. Yet their work reached directly onto the operating table, and the choices made in laboratories thousands of miles from the front line decided, with startling precision, which soldiers kept their limbs and which did not. To understand why this mattered, you first have to understand what infection did to a wounded man before 1943. In the First World War, roughly 90% of deaths among the wounded who survived to reach a hospital were caused not by the original injury, but by what grew inside it afterwards. Battlefield wounds are filthy by nature. Shrapnel drags uniform cloth, soil, and manure-fertilized farmland deep into muscle tissue. Bullets crush blood vessels and leave pockets of dead flesh with no oxygen supply, precisely the environment favored by Clostridium perfringens, the bacterium responsible for gas gangrene. Once established, this organism releases toxins that dissolve tissue and pump gas into the muscle at a rate that can be tracked almost hour by hour. Left untreated, mortality from established gas gangrene ran as high as 60%. The only remedy available to a First World War surgeon was radical debridement, cutting away every trace of damaged tissue, and if that failed, amputation performed high enough up the limb to stay ahead of the spreading infection. Soldiers arrived at base hospitals having already lost arms and legs not to the wound itself but to the race against rot. By the late 1930s, medicine had found one genuine weapon against bacterial infection. The sulfa drugs, sulfonamides derived from the German dye industry, and first proven effective in 1932 by Gerhard Domach. These drugs, sold under names like Prontosil and carried by soldiers in tablet and powder form, worked well enough against streptococcal infections and were credited with saving lives from pneumonia and blood poisoning. Winston Churchill himself was treated with the sulfa compound during a bout of pneumonia in 1943, and the drug's reputation among the public and the military alike had grown to the point where it was regarded as something close to a wonder cure. But sulfa drugs had a serious limitation that battlefield surgeons discovered the hard way. They were bacteriostatic rather than bactericidal, meaning they slowed bacterial reproduction rather than killing the organism outright, and they required a functioning blood supply to reach the site of infection. Gas gangrene, by definition, developed in tissue where blood supply had already been cut off by trauma. Dead muscle starved of oxygen and sealed away from the bloodstream that might otherwise have carried a drug to where it was needed. The drug simply could not get where it was needed. Surgeons who packed sulfa powder into gangrenous wounds in North Africa in 1942 found the disease progressed regardless, the telltale crackle of gas beneath the skin, spreading hour by hour no matter how much powder was applied. The gap between what medicine could treat and what battlefield wounds actually produced remained as wide as it had been in 1918. Something else was needed, something that could reach into dead and dying tissue and kill the organisms living there, and by the early years of the war, nobody was entirely sure such a thing could exist, let alone that it could be manufactured in the quantities an entire theater of war would demand. The answer had in fact already been sitting in a petri dish in London since 1928, when the bacteriologist Alexander Fleming noticed that a stray mold contaminating one of his cultures was killing the surrounding bacteria. Fleming named the active substance penicillin, published his findings, and then largely abandoned the work, unable to purify or stabilize the compound in useful quantities. It took a decade and a different team to turn that observation into medicine. At the Sir William Dunn School of Pathology in Oxford, the Australian pathologist Howard Florey, the German-born biochemist Ernst Chain, and a quietly brilliant technician named Norman Heatley rebuilt Fleming's mold culture from scratch, purified the compound, and by 1940 had proven in mice that penicillin could cure lethal bacterial infections without apparent toxicity. Britain, however, was fighting for its survival against the Luftwaffe and had neither the industrial capacity nor the chemical engineering expertise to manufacture penicillin on any meaningful scale. Florey and Heatley made the fateful decision to carry their mold, quite literally smeared into the linings of their coats in case the aircraft was searched, across the Atlantic to the United States in the summer of 1941. What happened next turned a laboratory curiosity into one of the largest pharmaceutical manufacturing programs in history. American researchers at the U.S. Department of Agriculture's Northern Regional Research Laboratory in Peoria, Illinois, went looking for a more productive strain of the mold and found it, almost unbelievably, on a moldy cantaloupe purchased at a local market. That strain produced roughly 200 times more penicillin than Fleming's original. Chemical engineers, including Margaret Hutchinson Rousseau, then solved the far harder problem of growing the mold at industrial scale, developing deep tank fermentation vessels, essentially colossal steel tanks of 25,000 gallons or more, that could culture the organism continuously rather than in the shallow surface trays used in Oxford. Pfizer built the first such plant in Brooklyn in 1943 and quickly became the largest single producer, its fermentation tanks not far removed in scale and appearance from a small brewery, humming around the clock. By the end of 1943, a dozen American pharmaceutical firms, later joined by British and Canadian manufacturers including Connaught Laboratories, were racing to expand output. The results were extraordinary. From a few 100 million units in 1943, production climbed into the billions of units per month within a year, and by the time of the Normandy landings in June 1944, an estimated 23 million doses stood ready for the invasion force. Precise total wartime output remains difficult to state with confidence, since much of the manufacturing data was treated as militarily sensitive at the time. But by any measure, the United States had achieved, in under 3 years, the transformation of a fragile laboratory compound into a mass-produced battlefield medicine. The drug itself worked by a mechanism unlike anything sulfa could offer. Penicillin interferes with the construction of bacterial cell walls, causing susceptible bacteria to rupture and die as they attempt to divide. Unlike the sulfa drugs, it was directly bactericidal, and it could be packed straight into a contaminated wound as a powder or delivered by injection into surrounding tissue, working even where blood flow was compromised. To picture the dose involved, a single treatment might amount to no more than a pinch of powder weighing a fraction of a gram, yet within that pinch lay enough biological force to halt an infection that a surgeon's knife alone could not reach. Surgeons in North Africa began testing it in earnest from mid-1943 onward, and stateside trials at Bushnell General Hospital in Utah and Halloran General Hospital in New York, treating soldiers with compound fractures and chronic bone infections that sulfa had failed to touch, produced results dramatic enough to convince the U.S. Army that penicillin was no longer experimental but essential. Early batches were far from pure, and the impurities in those first solutions caused painful inflammation at injection sites, a problem doctors gradually solved through better filtration as manufacturing techniques matured. Supply remained tight enough in 1943 that requests to use it for civilian illnesses, even cancer and meningitis, were routinely refused so stocks could be preserved for the wounded, and every vial that reached a field hospital in North Africa represented weeks of round-the-clock fermentation back in Brooklyn or Peoria. If you're finding this interesting, a quick subscribe helps more than you know. In the field, the effect on individual soldiers was described by surgeons almost in the language of miracle. Wounds that would once have been marked for amputation on site were instead debrided, packed with penicillin, and left to heal closed. Colonel S. W. Thompson, a Seaforth Highlander wounded in the thigh during the Sicily campaign in 1943, later recalled receiving the powdered drug directly into his wound as part of an early field trial and being back with his unit within 5 weeks, a recovery that would have been almost unthinkable a year earlier. Records from the 21st Army Group covering the Normandy campaign found that gas gangrene among Allied troops treated with penicillin occurred at a rate of only around 1.5 cases per 1,000 wounded, and that even those cases proved roughly half as likely to be fatal as gangrene had been earlier in the war. Exact figures on how many limbs were saved rather than lost are impossible to reconstruct with precision, since so much depended on the individual wound and the timing of treatment, but multiple wartime and post-war assessments converge on the same broad estimate. Penicillin prevented death or amputation in roughly 15% of severely wounded soldiers who received it, a proportion that, across the millions of Allied casualties in the European and Pacific theaters, translates into a staggering number of men who kept limbs that the medicine of a single generation earlier would have taken. Across no man's land, the picture looked very different. German military medicine had pioneered the sulfa drugs in the first place, and German field surgeons remained heavily dependent on them throughout the war, precisely because penicillin never reached German production lines in any meaningful quantity. This was not for lack of trying. E.G. Farben, the vast German chemical conglomerate that had built its wartime power on dyes, synthetic rubber, and pharmaceuticals, attempted to develop its own penicillin manufacturing process and reportedly sought to acquire mold strains and technical knowledge by whatever means available. It never succeeded in matching the fermentation techniques developed at Peoria and refined by American engineers, and German industrial coordination, fractured by rivalries between ministries and starved of the raw materials and stainless steel needed for deep tank fermentation as the war turned against Germany after 1943, could not replicate what American industry had achieved. The result was that penicillin remained, for practical purposes, unknown to German battlefield medicine for the remainder of the war. German surgeons compensated as best they could within the limits of sulfa treatment, and studies of German prisoners of war captured by Allied forces found gas gangrene rates running at 20 to 30 cases per 1,000 wounded, roughly 15 to 20 times higher than the rate recorded among penicillin-treated Allied soldiers in the same period. German Army medical reports from later in the war describe worsening shortages of blood and plasma alongside the absence of penicillin, conditions that left field hospitals reliant on debridement and amputation as their primary tools against infection, the same tools available to surgeons a quarter of a century earlier. In an unsettling postscript, The SS conducted experiments on prisoners at the Ravensbrück concentration camp, specifically to test whether sulfonamides could substitute for what penicillin offered, deliberately inflicting wounds and introducing bacteria and foreign material to study infection under controlled but grotesquely unethical conditions. Those experiments only confirmed what German surgeons already suspected from the front. Sulfa alone could not stop gas gangrene once it had taken hold, and no amount of German industrial ingenuity applied in 1944 could close a gap that had already been decided by decisions made in Oxford and Illinois years earlier. The material difference this produced was not simply a matter of medical statistics. It shaped how commanders thought about casualties, how quickly wounded men could be returned to duty, and how families on each side experienced the aftermath of the same battles. Allied wounded, treated with a drug that killed the infection at its source, could realistically expect to keep the limb they arrived with and stood a meaningfully better chance of returning home whole. German wounded, treated with a drug that could only slow what it could not kill, faced surgery decisions built around subtraction rather than preservation. It is worth being honest about the limits of this comparison. Survival and recovery depended on dozens of factors beyond antibiotics, including blood supply, evacuation speed, and surgical skill, all of which also deteriorated for Germany as the war ground on. But among battlefield surgeons and medical historians on both sides, penicillin is consistently identified as the single clearest medical dividing line between the two armies' capacity to save a wounded limb. None of this is to suggest the story ends in tidy statistics. Much of the detailed production data from 1943 and 1944 was classified at the time and never fully reconciled afterwards, so historians continue to work with estimates rather than exact totals for how many doses reached the front in any given month, and the 15% figure for amputations prevented is itself drawn from post-war assessment rather than a single wartime tally. What is not in dispute is the direction of the gap. Every account from Allied and German medical officers alike, whether drawn from official after-action reports or the recollections of individual surgeons, describes the same asymmetry. One army with a bactericidal drug it could manufacture by the billions of units a month, and another without it. The wider legacy of this gap reached well beyond 1945. Overall, Allied wounded who reached medical care alive survived at a rate approaching 50% by the war's end, compared with roughly 4% in the First World War, a shift owed in large part to penicillin and the blood transfusion and evacuation systems built alongside it. The techniques and manufacturing infrastructure developed at Peoria and by Pfizer became the template for the entire post-war antibiotic industry, and within a few years, dozens of related compounds followed penicillin into production. The triumph carried its own warning. Bacterial resistance to penicillin appeared within years of its introduction, a reminder that even the most decisive medical weapon has a limited shelf life against organisms that evolve. Original wartime penicillin production equipment and archival material can still be seen today at sites connected to Pfizer's Brooklyn plant history and in museum collections documenting the Oxford research, including artifacts held by the Science Museum in London, physical traces of a discovery that changed the outcome of surgery on an industrial scale. Return for a moment to that tent outside Gafsa in March 1943. The soldier on the table that night had no idea he was part of history. He knew only that the surgeon above him had made a choice that broke with everything battlefield medicine had taught for a generation, and that 6 weeks later he walked out on a leg the textbook said he should have lost. Multiply that single decision by the hundreds of thousands of Allied wounded who received the same treatment across North Africa, Italy, and Western Europe, and you begin to see the true shape of what penicillin achieved. It was not simply a drug. It was the difference between an army that amputated as a last resort and an army for whom amputation was, for the first time in the history of warfare, no longer the first resort. On one side of the line, surgeons reached for a scalpel because it was the only tool that had ever worked. On the other, they reached for a syringe, because for the first time, something finally did. The mold on an Illinois cantaloupe and the coats smuggled across the Atlantic had done what no army, however well equipped, could do alone. They had rewritten, in the space of 2 years, what it meant to survive a wound. And for every soldier who walked home on both legs because of it, that rewriting was the whole of the war. 2 armies fought across the same beaches, through the same olive groves and hedgerows, under the same shell fire. Both bled in the same ways. Only one had found in time a way to stop that bleeding from becoming a death sentence for the limb itself. That is the quiet, unglamorous victory hiding inside the larger one. One not with tanks or aircraft, but with a steel fermentation tank in Brooklyn and a mold that, by pure chance, had landed on a piece of fruit in an Illinois market. It saved legs. It saved arms. And in doing so, it saved the shape of an entire generation of men who came home from the war, whole,